Okay, next please. So I'm going to start with a few words about functional recovery. Could you put the next slide on the screen, please? Okay. This is an aerial photo of Christchurch Central Business District before the 2011 earthquake. Next, please. Oh, I can never stand. Thank you. So this is the same area 9 years after that. You see a lot of empty lots where buildings used to be. Only 2 buildings collapsed during this earthquake, but about 50,000 people were displaced. About 11% of businesses in this area were permanently closed. Per current building codes for new construction, this is completely acceptable. Why? Because what building code promises today for seismic safety for seismic performance of building is to reduce or minimize the likelihood of collapse. So only 2 buildings collapsed. So all of these buildings met their intended performance target per the new codes in the US and in New Zealand, right? But as I mentioned, there were severe consequences in terms of loss of jobs or access to schools, etc. So this would not be acceptable by the public anymore. Public would like to get back their businesses and schools and their homes in a shorter time frame after the event, after the earthquake. So we need to design our buildings better such that they can recover their functions within an acceptable time frame after the earthquake. And this is what we call functional recovery. The goal of functional recovery is to design buildings such that they can recover the basic functions in an acceptable time frame after the earthquake. And this need has been recognized by the federal government. So in 2018, Congress tasked NIST and FEMA to develop a report identifying options for improving the functional recovery of built environments. So through a big stakeholder engagement process, NIST and FEMA developed this report and submitted it to Congress in 2021. And since then, functional recovery design has been an emerging topic in our field. A lot of efforts have been done after submission of this report to Congress to address various recommendations from this report. Both NIST, FEMA, and other federal and non-federal agencies and organizations have done a lot of work on this. A notable effort that was led by Building Seismic Safety Council of NIPS was the development of a new functional recovery design chapter for the National Earthquake Hazard Reduction Program seismic design provisions. That chapter is completed and will appear in the next NEHAB seismic design provisions, and is currently under balloting at the ASC 7. In addition to that, there have been a lot of tools and frameworks been developed over the last few years. But there's still a big gap here. We still need more functional recovery data that is specifically collected to inform our design, our new design limits that we put into codes and standards. So in order to collect this data, we might need a different questionnaire. And you may say, okay, why do we need different questionnaire? We have a lot of questionnaire for collecting building performance after the earthquakes. We do have a lot of questionnaires out there, but the problem is that most of the questionnaires that are being used in reconnaissance efforts are primarily focused on building damage, and they do not go all the way to the building functionality and use. So we need to better understand the consequence of damage on the building functionality and use. We also need to collect recovery data at the asset level, at the building level. And the other issue that exists with the current reconnaissance questionnaire, some of them, is that they are all different. They collect inconsistent data, and it's really hard to combine the results at the end. And we need to standardize this data collection process in order to make sure that we can collect key data in a consistent manner that can inform development of future design codes and standards, and also validate and benchmark recovery time estimation methods. So in an effort to address this need, a group of colleagues and I developed a questionnaire specific to functional recovery. This group is Earthquake Engineering Research Institute Hausner class of 2020. I would like to acknowledge my colleagues who worked on this with me, Rahma Hanifa, Kiara McKinney, Maria Mohammed, and Lucy Arends. So we released this questionnaire on the EERI, Earthquake Engineering Research Institute website. Here's the QR code. If you're interested, you can take a look at it and learn more about it. Who can use this questionnaire? Anyone who is interested in collecting recovery data at the asset level and understanding the consequence of damage within the building on the building functionality and use. This questionnaire covers a variety of topics, including functionality checks, impeding and external factors, and also repair of the damaged components. In the next few slides, I will give you an overview of some of the key questions that we asked in this report, in this questionnaire, sorry, and why those questions matter. The key part of this questionnaire is a functionality check question. So in this section, the goal is to assess current functionality and usage of different systems or subsystems within a building to understand if they are performing or not. If not, what is the consequence of the lack of functionality of like water distribution system or water system or HVAC system on the functionality of the building. So in this section, for each of these systems, including water, HVAC, sewer, electrical system, we asked how long this system have been not functioning, and did the failure of the system impact the use of the building, and what caused the system to stop functioning. So these questions are asked in a different way. Here we are trying to understand the damage within each subsystem and connect it to the functionality of that subsystem all the way to the functionality of the building as a whole. So we have a set of questions that target different subsystems within a building. Another section in the questionnaire targets the architectural components and building contents. These are very important components for the functionality of the building. Architectural components include like cladding or sealing within a building, and building contents shown to be very important for functionality of certain buildings. So here the goal is to evaluate the performance of these components and their impact on the functionality of the building as a whole. So we asked the question of did failure of this architectural component, like cladding, impact the functionality of the building as a whole or not? How long did it take for this cladding to be repaired and for the building to regain its function? The next section is focused on repair and impeding factors. As you know, repair is a key component of the recovery. So in order to validate your recovery time estimation method, you need to have a good understanding of the repair processes and delays within that process. So in this section, we ask like building occupants or users, is there any plan to repair the building? Can the building be cleaned up and used after the event? This is an important question because a lot of minor damages can be cleaned up and the building can regain its function, and the repair can be scheduled for a later date, and that is great, right? So we need to understand that. Is there a permit required for this repair? Research done by researchers from Berkeley showed that as soon as the building permit is required for a repair, the recovery time may increase by 6 months to a year. So it's really important to identify where the building permit is required for the repair. And when the repairs is started or when they are finished, we want to have data on the recovery and repair time for different components within the building. And we also need to understand the delays. We ask participants, where are the delays in conducting this repair? Delays play a key role in the total recovery time of a building. And at the end, we ask questions to understand the causation of those delays, because of the financial issues or other things like contractor mobilization, things like that. So I encourage you to take a look at this, this questionnaire. This questionnaire is a seismic-specific questionnaire, but it can be leveraged for all other hazards. And like performance-based design, it started in the seismic world, and then other hazards started like leveraging that and adopting that concept. So functional recovery could be the next thing that is started in the seismic world, and later on will be leveraged and adopted for other hazards. And I think that has to be.
All right, thank you. So I'm going to pull a little bit further in terms of the data collection needs and talk about how we can use some projects that we're exploring at NIST now to try to support some of these research needs. So my name is Tanya Brown-Jamanco. I'm the director of the Disaster and Failure Studies program at NIST, and one of my key roles is to get people out into the field after a disaster so that they can collect the data that's needed for research or for investigations to help drive forward changes in code standards and practices. So as part of that, we've been exploring some ways to try to fill in some of those gaps by standardizing data collection approaches. So just a little bit about the program overall. Again, it's the Disaster and Failure Studies program. It gives us the ability to put teams out into the field to investigate building failures, infrastructure failures, emergency response and communications, evacuation procedures. We have a couple of different ways that we can do that, but the overall objective is to take these catastrophic events and try to learn as much as we possibly can from them so that we can improve code standards and practices. For some instances and under some authorities that we work under, we are basically required to see those through to completion. So if we come up with a recommendation based on one of our studies, we're required to work forward or work with other partners to make sure that it actually results in changes to those code standards and practices. So it's a very comprehensive program, kind of from the very beginning all the way to the end. And some of our initiatives have taken decades, to be honest, where we've conducted a study and worked through the initial research, and it's that last piece of changing that research into the codes and standards, which can cause a pretty long tail, but we've had some pretty big successes. We've had, when the program was started, was after the World Trade Center collapse, and of course we knew there was a terrorism issue there, but NIST was brought in to look at the engineering side of why the towers actually collapsed. And following that investigation, there were more than 40 code changes that have improved our building code since that time period. So it's something that we think is really important, really vital, and we're really proud of the successes that have been able to come from it. In addition to the Disaster and Failure Studies program, we've got two other programs in the natural disaster space that are congressionally authorized. Joel's going to talk a little bit more about NWRP, which is the National Windstorm Impact Reduction Program. And we've also got the National Earthquake Hazards Reduction Program. And those two programs bring together leaders within the federal space and are congressionally authorized for us to reduce the impacts caused by those kinds of events. They give us additional authorities to conduct our work, and we support a lot of different activities within these programs. So there's a lot of kind of cross-coordination and overlap in the work that we do. Steve mentioned this when he started, but he oversees our earthquake engineering group at NIST, and so there's a lot of coordination between our NEHRP group and his group so that we can help support each other in terms of the research and the congressional authorizations. So one of the things that I mentioned is that we're working on a project to try to bring data standardization forward. Right now, when there's a disaster event, if we need to send people out into the field, we've got cameras, we've got video cameras, we've got drones, we've got paper and pen. Sometimes we can quickly whip up an application on an app, a GIS-based app to collect some of the data that we think that we might need. But what we're trying to pursue going forward is to build out these tools as much as we can in advance. Now, of course, we don't always know exactly what's going to happen in any particular disaster or exactly what area of focus we might choose to look at in a given disaster. But the idea is that we want to go ahead and establish, to the extent possible, questionnaires, forms, data collection tools, so that when there is a disaster, we can get out quickly and we can get the data that are needed to move forward with our research and other objectives. And the idea is if we can collect a large amount of data using these kind of tools, that gives us a good statistical basis to conduct our analyses. The more and more data that we collect that is directly comparable, the better off we'll be in terms of generating statistics from those data sets. So one of our key objectives is to get geospatial data. We need to know where the data point came from, and we're wanting to get information on the hazard characteristics itself. So for example, in a flooding or a surge scenario, how deep was the water at a given point? How severe was the shaking associated with an earthquake? Can we get to a wind speed, or at least a wind speed estimation at a given geographical point? On the infrastructure side, we want to understand things that would sort of drive the performance of those. When was the infrastructure piece constructed? What codes or standards or practices or rules were in place at the time that the piece was put together? What are the materials that it's made of? What are the structural characteristics? How is it connected and put together? These are all data sets or pieces of data that can help us understand what things are working well, what things might not be working so well, where there are opportunities to improve the systems and the design of the systems. Also opportunities to support some of the functional recovery. If we can better understand how these things are or are not performing when they're most needed, that would be really helpful. Of course, we want to understand the damage and the cascading failures that come with these infrastructure damages. We also want to understand what worked when performance is good, and how the interconnection of some of these systems can lead to those cascading issues. One of the big ones that was talked about yesterday is kind of the backbone of infrastructure performance is power. In a lot of cases, the water system depends on power, the sewer system depends on power, the transportation systems may even depend on power for lights and things like that. So we want to understand the implications of those interconnected natures. And characterizing the larger and the ongoing social impacts by having those systems damaged or down for extended periods of time, and what that does in terms of limiting the ability for functional recovery of buildings that may otherwise be perfectly fine, but they don't have the systems necessary to continue operating. On the building side of things, there are some similarities. We want to understand when the building was constructed, what the codes and standards were in place at the time of construction. The basic characteristics, how big is the building, how tall is the building, what are the material characteristics, how valuable the building is, gives us a sense of scale of the kind of quality we might be working with, what its occupancy is, whether it's residential, industrial, manufacturing, those kinds of things. We want to understand how the building was put together. So what were the materials and connections? How well did it adhere to the building codes that were in place at the time? Are there key flaws or issues, things that were missing in terms of the construction? We want to understand the components and cladding. A lot of times the structural system may be perfectly fine, but the ability to continue to use the facility or to reoccupy the facility is often driven by losses to the components and cladding. Structurally, you may have a building that looks great, but every single window's been blown out. Well, okay, you're not going to be able to live and work in that kind of a building until all of those things get fixed. So we want to understand those components and claddings as well. We want to understand the structural and components and cladding performance in addition to what the components and cladding are. And this is the framework that we've put together to start driving our field data collection. So it starts with this idea that we're going to go out for a large variety of reconnaissance missions for lots of different kinds of hazards. It could be natural hazard driven, or there could be just a building failure or collapse that we need to assess. So within each of the areas that we might focus on in terms of the hazard, there are certain characteristics that we might want to get with regard to those things. And so we're trying to build this out in a modular framework where we've got a set of core questions that we're going to want for all different kinds of hazards and all different kinds of buildings and infrastructure. But when there are certain differences or certain key characteristics that are driven by the hazard or the building type, we want to build out modules so that we can ask in the questionnaires the information or ask the questions that are relevant for that particular study. There's no need to have a thousands of questions kind of survey where it's asking you a lot of information that's not relevant to the particular event or not relevant to the information that you're wanting to understand. So we're building it out in little modules so that you can pull the pieces and parts that you need for your particular study together. And the idea, again, being we want to drive this in terms of standardization to make this something that we publish so that we and others in the field could all collect data in a systematic and standardized way, which we think will help improve some of the analyses. So I'll pass it over to Joel.
All right. Thank you very much. Thanks to NIST for having me here. Joel Apply, I'm at NIST about a year and a half. Spent over 30 years with the National Weather Service. I'm a meteorologist and a tropical forecaster is mainly my background. But at NIST, I'm looking at all windstorms and helping to run this program that Congress had set up, the National Windstorm Impact Reduction Program, NWIRP. And first, define a windstorm. You know, of course it includes hurricanes, tornadoes, derechos, straight line winds, blizzards, but it also includes wildfires out west. That's their severe weather. The wind-driven wildfires in the urban interface is a big part of this. All the big fires that you can name in the last 8 years, Paradise, Boulder, Maui, Altadena, they've all been where winds have gotten up clearly over 50 and usually over 70 miles an hour, and people didn't have a lot of time to evacuate. So this program was started in 2004 and then reauthorized in 2014. It was originally put under the OMB to lead the program. Now it's under NIST as the lead agency. It says you will work with NOAA, of course the Weather Service and Office of Atmospheric Research, but NSF, FEMA, but then it says and other federal agencies. So one of the things that we've done since I've come over is work with other agencies to include things like power and transportation and look at the whole community resilience in that. So we've got NASA, the Department of Energy, look at power structures, Department of Energy, Office of Science, and Nuclear Regulatory, HUD, USGS. We've got Federal Highway Commission, Federal Highway Administration under DOT, and EPA as well involved in this. And a strategic plan was developed, and we put out a backward-looking report every 2 years to Congress, saying this is what we did and accomplished. But then there a couple of studies have been ongoing. When I walked in the door was Hurricane Ian that hit South Florida. There's a map of it there to the right. In 2022, Maria, of course, a big system that hit Puerto Rico in 2017. And looking at several different aspects of that, looking at how to communicate the information, be it probabilistic or deterministic type information, and working with NOAA and others to look at improvements to track forecasting and intensity forecasts. And let me be clear that there is a distinct difference between an absolute perfect forecast and people knowing the impact that's going to happen to them. And I've given thousands of interviews when it's going to be somebody's worst night in weather in their lifetime. And people don't want to believe that. So they look for information that fulfills that wish. I'm going to look for something that says that this isn't going to be the worst night of weather in my life. So they look at the cone and they say, well, I'm not right on the center line. Well, a hurricane is not a bullet, it's a bomb. So it doesn't have to exactly land on you for you to feel the impacts. So there's some changes going on to the cone this year. There's no center line. There's more inland watches in the mornings, and the cone now includes 90% chance instead of a 67% chance for that hurricane actually being inside that cone. So a lot of people look for reasons to think it's not going to happen to them, or that it's not going to be as bad as it's forecast, or it surely won't ever happen to me twice, or that it doesn't matter because the government's going to bail me out. Those are the four biggest lies after a big disaster. Some lessons from Helene. This picture was taken by my sister, who walked down to take a picture of her one of her neighbor's houses floating down the river close to Asheville, North Carolina. There was a big inland decay of winds after the storm moved in from Florida and through Georgia and some of the other southern states. The winds were 50, 60 miles an hour at tops, not hurricane force. And then it got to mountains of North Carolina, and there was a speed up impact from winds aloft being now at the surface through the mountains and valleys and slopes, and so a lot of trees were down. And recovery, functional recovery, is a phased effort. I've been to many disaster areas in many different countries, and it all comes down similar. One of the big things is, people want power, people want water immediately, and they want their home fixed or the community fixed. Well, there's a lot of things involved with doing that, and some of the things that we're trying to look at through this program and the efforts of all the different agencies. Each night you get on TV, and if you have a TV set and you're outside the impact area or the main impact area, the first thing they show is how many people are without power. So the power company doesn't like that, so they're trying to get power on as quick and in any way possible. And so what I saw in not a third world country, but in Asheville, North Carolina, was the power line was being put in by the power company, laying over the big tall oak trees and poplar trees. Just run that line and get the power on to that house so that we get off the evening news, and turn the light on. You can't live in the house, but the power's on, right? So they're just looking at numbers and that kind of thing. This event was so bad that the water pipes were no longer existent because they'd been washed away in the flood that occurred afterwards. And so people want to clear up the debris. That takes many months, 6, 9, 10 months. You got to find a place to put it, to burn it, to get rid of it, and open the roads up, get that internet back on, get the power on. 9 months after the hurricane hit, again, this is not a third world country, it's not an island, you still couldn't order a salad in Asheville because it didn't have running water to wash the lettuce, to put that back on, right? Many places then were going out of business because of that, and of course school had been in session, and the school system wants the schools opened up as quickly as possible. They don't want the kids to move away and not return. They get less money in the school system because there are less people in there, and that's federal assistance is very different today from FEMA than it was 2 years ago, and so that's a changing target and environment there as well. one of the bigger problems is after you get things back on and there is a functional recovery of the building, you still got to look at the community as well. You know, getting gas now becomes a problem. So when the gas station, the true story gas station, is located next to the kidney dialysis station. Well, there's a big long line that goes for a mile or more to get into the gas station. So when somebody pulls in front of you, they don't know that you're going to the kidney dialysis and your life depends on that. And in western North Carolina, there's a high likelihood that somebody in that truck that's waiting for the gas line for an hour, whose temperament is not the best in the world, has a gun in the car. So it became a problem for people to get the life-giving dialysis that they need because they're passing people up to get the gas. So a planning of the community too. People will build back as quick as they can. They want to move in their house. It's the only piece of property they own, right? Their whole life investment is in that house. So they're going to build back as quick as they can, which oftentimes means they build back the same and in the same location that got flooded out or something. So unless there's a code, a standard to prevent that or to make it better for them, they'll do it as quick and the same as they can. So those are the main points that I wanted to bring up, and thanks for allowing me to speak here.
Great, thanks everybody. So I just wanted to round out our session with some social science perspectives. My background is in anthropology and social ecological systems thinking, and I ended up at NIST in the earthquake engineering group, and I'm just super excited to be able to work with people who are in the engineering space and connect that back to humans and people and community needs. And in our risk reduction and recovery program at NIST, we also have a group that works on community resilience. So we're sort of in the whole spectrum of risk mitigation, resilience, recovery. We work on all of those things. So in terms of the societal impacts from earthquakes, most people are very familiar with building damage and can kind of understand all of those things. So we have the immediate deaths or injuries resulting from the event. But the other damage, downtime, interruption, and displacement that goes on drive these other consequences. And there are just some examples listed here in terms of first responder delays. Those are the types of things you're hearing on the news after an event occurs. There's weakened services by government and social systems. Healthcare can be impacted. Residents who live in older or unretrofitted buildings who have a lesser performance ability, are often more affected. Economic stability is impacted, of course. There's supply chain interruption, increasing costs. This helps to prolong the recovery trajectories. And then the will to adopt stricter codes and standards often happens after the event, right? There's the motivation to do that after the event, usually not before. And then, of course, cultural heritage and identity can be lost, sometimes permanently, in locations that have had significant impacts. So I just want to make a plug for any of you who can partner with other people who have expertise in social science. There's a number of disciplines, including economics, political science, geography, social work, etc. These are all people who are trained to think about human systems, the impacts to humans, and also have expertise in studying humans and gathering data from humans. So social science expertise can really advance engineering knowledge in terms of helping to inform the way that research is framed, both via theory or like why we think we should do a certain type of research, and also how, what methods are we using for that data collection. And obviously there are expertises in qualitative and quantitative data analysis approaches, and we really like to work on interviews and surveys, and we have expertise in putting them together and in trying to understand what is it that we really want to get at the end. You know, it's pretty easy to make a list of questions to ask somebody else. it's a little bit harder to figure out, once we have those answers, how are we interpreting them? And is that information really giving us, is it solving for the thing that we're really trying to solve for? And then, and obviously communicating research findings. So at NIST, I work both on the functional recovery topic and also on our investigation on impacts from Hurricane Maria in Puerto Rico, specifically related to emergency communications. And in addition to thinking about sort of emergency communications, I'm thinking about how does this relate back to our mission to work on engineering topics as well. So when we're thinking about reconnaissance or we're thinking about long-term investigations, we are conducting work with humans. And that's called human subjects research, and there's a whole set of protocols and ethical procedures in the social sciences for handling that type of research. And so I just wanted to highlight some training that is available from the Natural Hazards Center and the Converge modules on aspects that can help you to understand the research framing behind human subjects research. So for example, the questionnaire that CMAC mentioned related to functional recovery in the Hausner questionnaire, that questionnaire we had to put through our institutional review board at NIST and have it be approved as an instrument that we can utilize. So in terms of the modules that Tanya was talking about, many of these things, there's pre-approval processes that we have to go through in order to be able to use them, which just sort of adds to the research complexity. So for functional recovery specifically, in thinking about, okay, we've had an event, we want to collect data not only on the immediate impacts, but these longer trajectories of recovery, what do we need to strengthen? And some of the things that we're looking at in our ongoing work are thinking about our sampling strategies. How do we capture the damage and delay? The good examples of recovery that Tanya mentioned. How do we capture the data over time? What return period? Do we need to collect data every 6 months, every year, every 10 years? For some of these very large events, the recovery trajectories extend decades. And then the partnership procedures in order to collect the data. If you guys are not familiar with NEHRP, the National Earthquake Hazards Reduction Program, for our federal agency partnership, the USGS is actually responsible for initiating reconnaissance missions. And there's an entire procedure that we go through, and we have calls to coordinate on the reconnaissance, and there are a number of procedures, but the partnership aspect is really key, and that's both with who you're partnering to collect the data and who you're partnering with to gather the data, the people that you are interviewing or seeking information from. And in some cases, you want data from users of buildings, and in some cases, you want data from managers of buildings or people who are developers of buildings. So it can get kind of complex. And then one of the big things that we want to work on solving is in connecting asset level data to community outcomes. We want to strengthen community resilience. We want to strengthen, household business, et cetera, recovery. But when we're collecting data on a particular asset, how can we be sure that that data is going to be able to give us information about those larger scales? So those are some of the questions that we're sort of grappling with right now in correlating this data. And then in the end, the functional recovery performance objectives that are being sort of put into place now, we want to understand better in the future. How do we improve them? Or what have we learned from particular events that can strengthen them? And throughout the development of the functional recovery performance objectives, since we began in 2018, we have had involvement of a number of social scientists, and we've also held a number of workshops with subject matter experts. And those types of workshops and interactions that sort of bring a number of sectors together are how essentially the initial targets for recovery have been defined. And we didn't really get into some of that in this presentation, but we do have a workshop report out, and you can email me if you want some more information on the specific recovery times that have been identified or suggested for particular types of assets. So that's a different presentation. So with that, I'll wrap up, and we do have some time for questions. If you'd like to go ahead and take just a picture of this screen, in case you want to get in touch with any of us, please feel free. And thank you so much for being here.
Let's give them a round of applause. So I have a mic here. If you have a question, just raise your hand. I'll come over with the mic.
I have a question like what kind of facility are you mostly focused on, like collecting, and what would be the most important insights you want to get from this analysis?
I'll go ahead and kind of take a first stab and then let others join in. One of the key themes that we've been focusing on kind of throughout our department is the functionality and the damage and the ability to continue serving the community for schools and hospitals. Those being such a key community center, they're really critical for keeping the community together and providing the services that are needed within the communities. So a lot of our studies over the past 10 years or so have really focused on those facilities in particular, and how quickly they are able to come back up to full speed and full operation, or in the case of hospitals, never losing functionality in some of these events is really key. So a lot of our studies have focused on that recently, but any others you all want to mention?
Well, that's right. The other thing that I think is very important, other than schools and healthcare system, is like housing is super important, and jobs. These two are the other two components that are important and should be studied. But as you said, we have been more focused on healthcare and schools in our efforts.
I think we have the flexibility to kind of look at whatever we want depending on the particular event.
Hi, I'm Dara Naderi from Thornton Study. I'm wondering how we are balancing functional recovery with the cost of construction, and how is the recommendations based on a certain return period, or are we recommending that buildings be designed for functional recovery even for the ultimate load cases that we look at?
So in terms of cost, this is something that still needs to be studied further. We have done extensive work to answer that question, and we have a few publications under review for that. Our results show that for certain occupancy types, the increase in the cost would be between 2 to 6% construction costs. But for certain systems, we look at concrete moment frames, shear walls, BRBs, and steel moment frames. So that's the range that we are thinking. And these numbers are for a specific functional recovery design. They are not for the functional recovery design limits that are in the NEHA provision. So we are planning to utilize those design recommendations from NEHA side design provisions to answer the cost questions. In terms of hazard, as part of the ESSC work that I mentioned that developed the functional recovery design appendix for NEHA provision, there was a subcommittee or task committee looking at the hazard, identifying what is the appropriate hazard level that should be considered for functional recovery design. And In seismic world, we use the uniform risk approach, and for life safety design, so we have a target reliability level. We use the same approach, but with a different target reliability level, like 10% in 50 years of losing functions. And we introduce an FRER ground motion level, which if you look at that and compare that with the design level earthquake map, and it's either equal to design level earthquake or lower than that. In many locations, the FRER, functional recovery earthquake, is lower than the design level earthquake. So I hope I answered your question.
Yeah, Scotty Galloway, Great Consulting. I guess the one question I would have for each of you is, what is the one thing, if you could execute it tomorrow, what is the biggest obstacle that keeps you from achieving your ultimate objective?
Maybe I'll answer that two ways. I'll take the what I presented on the data collection side, and the thing that limits us right now is time. We're really busy and stretched thin, like many people are, and dedicating the time to gather the inputted information and understand what the true needs of our colleagues are in putting together these data collection platforms. That's a true limitation for us right now, because we're trying to also support some of the ongoing investigations that are still occurring. Taking that hat off and just saying kind of pie in the sky, overall objectives, beyond just the data collection side. I think in a lot of ways, as engineers and scientists, we understand a lot of things that could be done to improve construction, the ability for communities to recover and thrive and continue to use the buildings and the infrastructure. I think in a lot of ways we know what to do, and turning that knowledge into reality or practice where the steps are taken in advance to make sure that the resiliency is built in is still a pretty hard challenge. And trying to drive consumer awareness and demand of that is still really hard.
And I'll jump in to follow up on that a little bit. So from the social science perspective, I think a lot about individuals and families and communities. And so this gets also back to something Joel said. I think one of the biggest challenges actually is that people who use buildings and other infrastructure, they don't really know what performance they can expect from that infrastructure or house. The example would be that we do tons of forecasts about the wind speeds that are associated with a particular hurricane. But how does that person in that house know if their house could potentially withstand those numbers or not? Now, solving that problem, how do we do that? That's very, very complicated. But I think without giving people the tools to understand the potential performance, we're sort of asking them to make uninformed decisions about if they're going to stay, if they're going to go, if their house needs to be upgraded, et cetera. And I think, I'll leave that there.
To follow up on that, I think sometimes we can not see the trees because of the forest. This is we must look at the buildings. We must look at the resilience of the buildings, but we can't lose the sight of the fact that it's a community we're trying to get back up. And so that's why we want to work with so many other federal partners, agencies. They all have a different mission space. They all look at disasters differently, and they should. And so getting everybody in the same room and having those conversations takes time. Build trust. Engineering problem, clearly. It's a meteorological problem, clearly, but it's a personal problem. So you have to take time to build those relationships and that trust to get people to look at the disaster holistically, and then come up with reasonable solutions that people will actually utilize.
So to me, from the reconnaissance data collection perspective, one of the most important things is that we collect data, we collect the key data at different scales in a way that they are interconnected, and we can study the impact of one scale on another scale. So community resilience is the ultimate goal. Functional recovery is a mean to achieve community resilience. We don't build or design community as a whole, we build individual assets and they form community, right? But our goal for functional recovery is to improve community resilience. So it's important to collect data at multiple scales, at the community scale and also at the asset level scale, the individual building scale. And in a way that you understand the relationship, you understand how the lack of function, how this damage to this building can impact the function of the building, and how the lack of function of this building cluster that serve a specific community function impact the community as a whole, how it impacts the population displacement and things like that. So that's a big challenge in my view.
You can just state your name and who you are.
Sophia Fernandez, student at Arizona State University. You mentioned building microsystems and like the functionality of systems like the electrical and plumbing within a building earlier. And I was wondering about the relationship between overall infrastructure functionality and the functionality of individual buildings or a community as a whole.
Yeah, that's a very good point. The questionnaire that I shared is focused on the building level. It touches on the lifeline systems, but lifeline system is a separate topic connected to the building. So it was very hard for us to look at both buildings and infrastructure system. But in terms of infrastructure systems and lifeline, we look at them in terms of their connection to individual buildings and how our goal was to understand if the lack of functionality of the water, of the piping or water system within the building is because of the damage of the piping within the building, or is it because of the failure 2 blocks down the road, main water pipe? So we try to collect that data, and it's really important to understand this connection of how the lifeline system, distributed lifeline system, provide these services to individual buildings. And at some point, it may not matter much how good of a building you design and build, if you don't have water in the pipes, right? So it's important to collect that information. But for our questionnaire, that was considered a little bit out of the scope, so we focused on the building boundary, whatever is within the building boundary.
Yeah, because the design of the infrastructure systems are handled very differently than buildings, we do have a 2-volume report that is designed to help owner-operators of infrastructure systems go through a decision-making process in order to help them define what their functional recovery goals would be for the system, and to sort of procedurally go down to what then would be the component design, or what alterations or upgrades could they make to the system in order to enhance the functional recovery performance. But that gap between the infrastructure system and the buildings is something that we need to work on a lot more.
We have maybe one quick question.
Hi, this is Evelyn Fujimoto. I'm one from Lives Forward. My question is, do you think at some point in time you'll be able to take the data that you've collected and then maybe model other communities that have similar characteristics, and then be able to go to them and say, hey, if you can harden these 4 or 5 things, you will be in a better shape than, say, Asheville was?
Yeah, I think that's exactly some of the purposes that we can use these data for, so that we can understand kind of the key characteristics, the performance metrics, and yeah, there's actually some modeling that's been done within our, well, it just wrapped up our Center of Excellence, which is established at Colorado State, that is trying to do some of those things and understand how communities respond and recover from disaster events. And yeah, filling in any of the data gaps in terms of the performance of the buildings and the infrastructure, I think can be really key in doing what you just described, helping communities identify the steps that they can take and the key priorities to take those forward, and especially in an environment with limited resources, they're likely going to have to prioritize.
I think that's it for now. Let's give these panelists a round of applause. So now we're going into our break, and please come back at 11:15 for the housing case study. The industrialized construction breakout session.
Yeah.